following computer animation shows the way earth pressure balance shields work. Taking as an example the Heron Connect EPB shield used for a subway construction project in Barcelona. As part of the extension of Subway Line 9, the machine S442 excavates a 3.6-kilometer-long section between the subway stations Gornal and Zona Universitaria. The tunnel route crosses beneath Barcelona's historic city center, densely populated residential areas and roads. In order to avoid any damage to the sensitive buildings, subsidence, heave, and vibrations must be avoided at all costs. In addition, the impact on traffic above ground must remain as small as possible. The S442 is a classic EPB machine with an outer diameter of 12.06 meters and a total length of 95 meters. With its rotating cutting wheel, the tunneling machine breaks the material from the tunnel face. The material is then transferred to the belt conveyor system in the rear of the shield via a screw conveyor, while the hydraulic cylinders press the machine forward continuously. The reinforced concrete segments, known as lining segments, are installed under the protection of the shield skin. When the ring building has been completed, the machine can push itself against the new tunnel ring and drill further into the soil. The 83-meter-long backup accommodates all logistic facilities necessary for the operation of the overall system. The working method of an EPB shield is basically made up of two phases: the tunneling phase and the ring building phase. During the tunneling phase, the cutting wheel, which rotates at a speed of up to 2.7 revolutions per minute, is pressed against the tunnel face with a pressure of up to 400 bar by means of hydraulic cylinders. 24 hydraulic motors drive the cutting wheel via a gear rim, developing a drilling torque of up to 38,000 kilonewton meters. Under this high pressure, the disc cutters and cutting knives made of high-strength steel loosen the material at the tunnel face. If necessary, the soil can be conditioned with water, bentonite, or foam using the injection systems located on the backup. With the help of nozzles integrated into the cutting wheel, the corresponding conditioning medium is injected into the soil, which is pressed into the excavation chamber by the existing earth and groundwater pressure. For shield tunneling in non-stable soils, a loss in stability at the tunnel face is compensated by creating a support pressure. In the case of the earth pressure balance shield, the soil which was excavated by the cutting wheel is used to support the tunnel face. In order to reach a state of equilibrium, the support pressure is transferred by the hydraulic cylinders via the bulkhead to the soil, which avoids an uncontrolled penetration. The soil prepared in this way can now be transported from the invert area of the excavation chamber to a belt conveyor by a screw conveyor. The screw conveyor is driven by two hydraulic motors which have a power of up to 400 kilowatts. The quality of the soil taken from the excavation chamber is regulated by the screw conveyor's rotational speed, which is matched to the advance speed. The aim is to maintain a state of equilibrium between the quantity of soil removed by the screw conveyor and the quantity of soil accumulated from the shield's tunneling process. This guarantees optimum support for the tunnel face. The system must be able to react flexibly to the permanently changing geological conditions. Therefore, the current state is continuously controlled with the help of pressure sensors, by measuring the cutting wheel torque and the screw conveyor torque, and by monitoring the excavated material. When the tunneling phase is completed, cutting wheel and screw conveyor are stopped. Now the ring building phase starts in the shield area under atmospheric pressure conditions. A complete tunnel ring consists of several segments, called lining segments. These prefabricated reinforced concrete elements are produced with millimeter precision in a factory which is especially installed above ground for this purpose. Following quality control, they are then transported into the tunnel by mine cars. In the front section of the backup, the lining segments are lifted individually by a special transfer crane. It lifts them onto the segment feeder which transports the elements to the front of the tunnel. Here, the heavy ring segments are picked up and positioned by a hydraulically controlled crane arm, called the erector, using vacuum plates. The erector is installed on 2 rails and can be moved, rotated, and telescoped. Each completed tunnel ring consists of several segments, 2 lateral elements, and the key segment, which is installed last. The positioning of the segments always follows the same routine. The erector lifts the stone from the segment feeder. The hydraulic cylinders are then retracted from the corresponding installation point. The segment is positioned precisely, holding sight contact next to the previous installed ring, using a remote control. Now the hydraulic cylinders are extended again to secure the segment in its position and to subsequently bolt it into the previous ring. During this process, machine and tunneling personnel are protected by the shield skin against the earth pressure and any possible groundwater. In this way, the lining segments are installed on each side alternately. The key segment, with its tapered sides, is slotted into position last and distributes the loads in the ring, completing the ring building. Subsequently, the next tunneling phase can start. The end of the shield, the so-called tail skin, is equipped with a circular tail skin sealing. This provides a seal between the sealed structure of the shield machine and the segment ring. This in turn guarantees the necessary sealing between the interior working space and the exterior earth pressure. The remaining annular gap between the outer side of the lining segments and the soil is continuously filled with grout via injection holes in the tail skin or in the lining segment in order to provide a bed for the tunnel tube and to stabilize it. Each individual tunnel ring is constructed in a slightly conical form. This means that curves can be constructed along the tunnel route by changing the installation position. A time-lapse clearly shows the 2 working phases of the TBM. The tunneling phase and the ring-building phase alternate continuously. In this way, the tunnel grows ring by ring. Under optimum conditions, up to 350 meters of tunnel can be constructed in 1 week. This includes the removal of up to 40,000 cubic meters of excavated material and the installation of far more than 1,000 lining segments. Complex logistic solutions are required to deal with such quantities of material. The 83-meter-long backup of the S442 tunnel boring machine accommodates all the facilities required. With each advanced movement of the shield skin, the backup is pulled behind on wheel houses, which brace against the tunnel wall. Among other things, the steel structure accommodates hydraulic power units, pumps, switch cabinets, ventilation systems, laser instrumentation, and storage containers for soil containers. In addition, logistic solutions for the delivery of the lining segments and the removal of the excavated material are located here. All important data and up-to-date tunneling parameters are gathered together in the central control cabin. There, they are visualized on monitors and made available to the machine operator. The operator can monitor the largely automated process and intervene if necessary. In the case of EPB machines, the excavated material is mostly removed by belt conveyors. The core components of such systems are the machine belt, the cross belt, and the tunnel belt, which can measure up to 30 kilometers. The machine belt and the cross belt are two separate short conveyors which are permanently installed on the tunnel boring machine. The tunnel belt takes up the excavated material from the cross belt in the backup area and transports it along the total tunnel section to the launch shaft. The front section of the tunnel belt is also permanently mounted on the backup. The rear part is statically mounted on the tunnel wall and is continuously extended during the ring building phases to match the growing conveyor distance. In order to compensate for the increase in the conveying distance, a special belt storage system is installed at the launch shaft, which releases the extension of the tunnel belt as required. The cutting tools must be maintained or replaced in regular intervals, depending on the hardness and abrasiveness of the geology. Sensors are attached at the tips of some tools, which trigger an alarm in the control cabin when a certain degree of wear is reached. If a tool must be replaced, the excavation chamber is partially emptied. At the same time, the cavity in the chamber is supplied with compressed air, if necessary, to stabilize the tunnel face. Then the excavation chamber can be accessed through a manlock to carry out maintenance work or to replace tools. A disc cutter is exchanged in 3 steps. Initially, the quick-release fasteners are loosened. Subsequently, the disc cutter is pulled out of its support with a special tool and, in a 3rd step, replaced by a new one. Traditionally, earth pressure balance shields made by מכונת are in their element in cohesive soils consisting of clay and silt with low water permeability. Moreover, loose soils consisting of sand and gravel and unstable rock can also be successfully mastered with the EPB technology.